Good morning to all. We have talked about the topic real analysis. We shall now discuss the concept of functions of bounded variation, which is closely associated to the concept of monotonic function and has wide applications in mathematics. These functions are used Riemann-Stieltjes integral and Fourier series. First, we shall talk the topic functions of bounded variation. Let a function define the interval closed interval of a comma b and b equal to a comma b equal to x naught x1 up to etc xn be a partition of a comma b. Consider the sum of summation I equal to 1 to n f of xi minus f of xi minus 1. The set of sums is infinite. In the set of bounded above, the functions f is said to be a bounded variations, and the supremum of set is called total variations of function f on a comma b and is denoted b of f into a comma b or bf of a comma b, vf or vf. Thus Vf of a comma b equal to supremum of I equal to 1 to n modulus of f of xi minus f of xi minus 1. Hence, the functions f is said to be of bounded variations of a comma b if and only if it is total variations is finite. V of f of a comma b less than infinity. Theorems. A bounded monotonic function is function of bounded variation. Given f bounded monotonic functions. Suppose a function f is monotonic increasing on a comma b, then partition b exists. P equal to x naught x1 up to etc xn. Summation I equal to 1 to n f of xi minus f of xi minus 1 equal to summation I equal to 1 to n f of xi minus f of xi minus 1 equal to f of b minus f of a. V f of a comma b equal to total variations of f of a comma b equal to supremum of summation f of xi minus f of xi minus 1. F of xi consider the first initial point of a and f of xi minus 1 is considered the last point of b. Apply f of xi equal to f of a minus f of b. Hence the functions f is bounded variations on a comma b. Similarly, a monotonic increasing bounded functions if bounded variations with total variations f of a minus f of b. Thus, for a bounded monotonic functions f, Vf equal to modulus of f of b minus f of a. The next theorem, if the derivations of the functions f exist and is bounded on a comma b, then f of bounded variation on a comma b. First, let us the theorem given is the derivative functions f exist. We have to prove that f is bounded variations on a comma b. Then the derivations of bounded variations f exist, then f dash is bounded on a comma b. There exists a k such that modulus of f dash of x less than k for all x belongs to a comma b, which is the definition of derivative. Again, the bounded variation, the partition exists p equal to x naught up to etc xn. Summation model of f of xi minus f of xi minus 1 equal to summation modulus of xi minus xi minus 1 f dash of c. C belongs to closed interval of a comma b. Then less than or equal to k modulus of b minus a. B of f of a comma b is finite, then f is bounded variations on a comma b. A functions are bounded variations necessary bounded. The properties of bounded variations. The sum of difference of two functions of bounded variations is also bounded variations. The second property is the product of two functions bounded variations is also bounded variations. The third property is if f is functions of bounded variations on a comma b and if there exists a positive number k such that modulus of f of x greater than or equal to k for all x belongs to a comma b, then 1 by f is also bounded variations on a comma b. If f is bounded variations on a comma b, then it is also bounded variations on a comma c and c comma b, whereas c is a point of a comma b, and conversely also total variations of v of f comma a comma b equal to v of f of a comma c plus v of f of c comma b. The next talk about the topic variations of functions. Let f be a functions of bounded variations on a comma b and x is a point of a comma b. The total variation v of f comma a of x on a comma b. Then the total variation is called simple variations of function f and it is denoted v of f of x. When there is no scope of confusion is simply write as v of x. Then we consider the theorems. A functions of bounded variation is expressible as the difference of two monotonic increasing functions. F of x be a functions f of x equal to 1 divided by 2 v of x plus f of x minus 1 divided by 2 v of x minus f of x. We shall prove that two functions g of x, h of x has monotonically increasing on a comma b. Now if x2 greater than or equal to x1, we have g of x2 minus g of x1 equal to 1 by 2 v of x2 minus v of x1 plus f of x2 minus f of x1. Since v of f comma x1 x2 greater than or equal to f of x1 minus x2, this implies g of x1 g of x2 greater than or equal to 0. Show that the function g of x is monotonically increasing on a comma b. Again, similar the part of h of x1 and h of x2 is also monotonically increasing functions on a comma b. Note, a function f of x is bounded variations over the interval a comma b if and only if it can be expressed different of two monotonic functions. Next theorem. Let f be a bounded variations on a comma b. Let v define on a comma b as